we had our basic session on rotational dynamics. Although, I cramped a lot of stuff in one session for you, but I almost presume that you understand the stuff that was covered in the class on rotational dynamics, right? Can I assume that? Is there any concept that still is hazy or difficult to comprehend? So what we'll do is, we'll take a little bit of a practical approach to things. We'll cover rotational dynamics in stages through problem solving, and then get back to some theory concepts and stuff, so on and so forth, right? If you recall, I'd covered the basic ideas on rolling without slipping, right? Remember that? Now, let me look at some variations around that. Let's say this is a disk of mass m and radius r. A disk of mass m and radius r. And on a fixed horizontal surface that is rough, that has friction. Mu is the coefficient of friction on this rough horizontal surface. And we set it into a state of pure translation. We set it up in a state of pure translation. Pure translation means all particles constituting the system will share a common velocity with the center of mass, right? Let's say the center of mass, this is time t equal to 0. When I set it up in pure translation, and the center of mass has a velocity v0, and all other particles constituting the rigid body would be deemed to have the same velocity v0, So this is a state of pure translation. Now let's see what happens beyond this point. Let's examine what transpires beyond this point. Look at the point of contact. The point of contact has a rightward velocity. There is relative motion between the body at the point of contact and the surface, right? And therefore, kinetic friction would act on this. Body, and would, if this point on the rigid body has a velocity v0 to the right, then the frictional force at this point of contact on the body will act leftward, and it would be kinetic in nature, and therefore approximately equal to maximum static. Now, very clearly then, frictional force F equal to mu mg acts on it leftward, where mu is the coefficient of static friction, but mu mg approximately equal to kinetic friction as well. Maximum static friction and kinetic friction, for all practical purposes, could be assumed to be practically the same. Now, the effect of this frictional force acting leftwards. Let's examine that. Well, as far as the center of mass is concerned, it has a velocity v0 to the right, and it will experience a retardation. The center of mass will experience a retardation because of this frictional force. The retardation would be mu g. The net effect of a certain force in terms of translation is felt by the center of mass, is represented by the center So the center of mass experiences a leftward force mu mg and therefore a leftward retardation mu g. It experiences a leftward acceleration and therefore retardation equal to mu g. Mu g leftwards is what it experiences, right? Now, so this A is in opposition to V naught and therefore it's going to kill V naught. It's therefore going to kill V naught, yes or no, right? So the velocity of the center of mass will decrease because of this retardation mu g, because of this retardation mu g. Now, the other effect. Well, the sum total of all the forces acting on this rigid body would be, there is one frictional force acting leftward, there would be normal reaction N acting upwards, and there is going to be mg acting downwards, N balancing mg. This is the sum total of all the forces. Now, what's the torque of mg about the center of mass? 0, because the line of action of mg passes through the center of mass. What's the torque of n about the center of mass? 0, because the line of action of n passes through the center of mass. But what's the torque that mu mg produces about the center of mass? Mu mg into radius r, and clockwise, right? So there is a clockwise torque about the center of mass, tau about the center of mass, that's equal to mu mg, which is the frictional force, into the moment arm r, Yes or no? Now, this clockwise torque about the center of mass produces a clockwise angular acceleration, produces a clockwise alpha angular acceleration clockwise, right? This clockwise angular acceleration will produce a clockwise angular velocity, yes or no? A clockwise alpha. If initial angular velocity is 0, will produce a clockwise angular velocity. So which means in a period of time, VCM, velocity of the center of mass, will decrease because of this retardation effect, and the omega clockwise will increase because of clockwise angular acceleration, or clockwise omega would develop, Now, so t seconds later, there would be a velocity of the center of mass obtained by V equal to u plus at, initial velocity v naught, retardation mu g, so v naught minus mu g into t, v equal to u plus at, clear? And there is going to be a clockwise omega that would develop, where omega would be initial omega plus alpha t, omega equal to omega naught plus alpha t, that would be omega. So let's first calculate alpha. And by the way, to calculate alpha, you would take recourse to tau equal to I alpha, but it has limitations. There are only two pertinent points about which you could apply tau equal to I alpha. One is the center of mass and about the instantaneous center. You can take torques about any point, not an issue, but tau equal to I alpha has limitations. It could be applied only about 2 points on the rigid body in general motion, one about the center of mass, two about the, and in either case, you will get the same value of alpha. Right? So let's calculate the angular acceleration so that we could eventually calculate the angular velocity at an instant of time t. So angular acceleration alpha is going to be tau about the center of mass divided by I about the center of mass. Tau equal to I alpha about the center of mass. Now, tau about the center of mass is mu mg into r. Is mu mg into r? Yes or no? Right? I about the center of mass is half mr squared for a disk. For a disk, if it was a sphere, it would have been 2/5 mr square. If it was a ring, it would have been mr square. But now that we have selected a disk, only for the sake of definiteness, it's going to be half mr square. It's going to be half mr square. So then, this turns out to be 2 mu g by r. This turns out to be 2 mu g by r. Clockwise angular acceleration. The clockwise angular acceleration, right? And this gives us a fair opportunity to be able to compute the value of omega at an instant of time t. Omega at an instant of time t would be initial omega 0 because we started in a state of pure translation. So initial omega was 0. So 0 plus alpha t. 0 plus alpha t would be the value of omega at an instant of time t. Yes or no? So alpha is 2 mu g by r into t. That's omega at an instant of time t. VCM at an instant of time t is known to us. Omega is increasing with time. VCM is increasing with. Look at how friction really acts. You know, it's a very basic premise of friction, very basic trait and character of friction. You know, when we started the whole scenario, the translation effect was pronounced, the rotational effect was weak. There was no rotation. So rotation was the weaker aspect of the motion, translation was the stronger aspect of motion. Yes or no? Right? What did friction do? Well, friction acted in a manner that it provided a mu g that weakened the stronger and strengthened the weaker, so that it could bring the two at parity in harmony. This is what friction would try and do. Friction, even though it seemed like rough and bad, but you know, the objective of friction is very fair. It wants to bring parity. It wants to bring harmony eventually. That's why it acts. All right. So then, with a view to bring about harmony, omega, the rotational effect increases, the translational effect decreases, right? So then, this is omega. This is omega. Look at omega r. Omega into r is like a 2 mu gt. It's like a 2 mu gt. It increases linearly with time. It increases linearly with time. VCM, V naught minus mu gt. It decreases with time. It decreases with time. Essentially then, realize that VCM decreases with time like this. Starts with a V naught and it gradually decreases. Omega r, this is VCM. This is how VCM is changing with time, linearly decreasing. Omega r is linearly increasing. And do you realize that at some instant of time t naught, VCM becomes equal to omega r. At some instant of time t naught, VCM becomes equal to r omega. Yes or no? And if VCM becomes equal to r omega, rolling would have commenced. You know what I'm saying? Rolling would have commenced. So all that friction did was to initiate and promote rolling conditions. It acted in a manner so that in this case, the VCM decreased, the omega r increased. Eventually, VCM became equal to r omega and rolling commenced. So, at an instant of time t naught, when rolling commences, at an instant of time t naught, when rolling commences, VCM becomes equal to r omega. So at t naught means at t naught omega r becomes equal to 2 mu g t naught. So VCM becomes equal to r omega. That means VCM, which is like V naught minus mu g into t naught, that's VCM. and R omega is 2 mu g T naught. R omega is 2 mu g T naught. So this will give us an opportunity to calculate the instant of time T naught when rolling would have commenced. So at time T naught when rolling commences, this is just some intermediate instant of time. At a later instant of time, rolling would have occurred. So this T naught is like V naught by 3 mu g. V naught by 3 mu g. Right? So the important thing is that if mu was higher, it would have taken lesser time for rolling to start. Right? That means friction is a very, very good friend of rolling. Friction would always act in a manner so that rolling is promoted. The higher the value of mu, quicker is the rolling condition commencing. Right? So, if it's a very, very rough surface, theoretically surface with infinite mu, then the time it takes for rolling would be 0. So, even though you might attempt to translate the body, it would instantly begin to roll. If it's a very, very rough surface means mu very, very high. Mu very, very high means T naught very, very small. And right away, your attempt to produce translation would fail. It will instantly start to roll. You know what I'm saying? Now, look, this is not necessarily the state where rolling occurs. This could be any state between this state and the state where rolling takes place. This is an intermediate state, right? Any state between this state and the rolling state. Realize that frictional force produces no torque about the point of contact because its line of action passes through the point of contact. mg passes through the point of contact, so it produces no torque about the point of contact. N passes through the point of contact, therefore it produces no torque about the point of contact. Which means on this rigid body, the net torque about the point of contact is, if the net torque about the point of contact is 0, that means the angular momentum about the point of contact must be constant, right? So the net torque about the point of contact being 0 causes the angular momentum about the point of contact to be constant, right? Now, when we started the entire business, translation, and if I have to compute the angular momentum about the point of contact, then it's simply going to be mv naught into r. There was no omega. Mv naught into r was the angular momentum about the point of contact, right? So initial angular momentum is mv naught into r. Mv naught into r about the point of contact, initial angular momentum. Finally means at an instant of time t. At an instant of time t. Look, if I have to, you should have a recollection of how we calculated angular momentum about various points for a rigid body in general motion. If you recall, and if you fail to recall right now, I would very strongly urge all of you, after I solve this problem, to flip through those pages where I discussed at length how one could calculate the angular momentum for various situations on a rigid body, right? So in this case, the angular momentum, because of pure translation, mvcm into r plus icm omega, right? And I enjoy the luxury of equating these two. Li equal to Lt. Means mv naught into r is mvcm into r plus icm omega, right? Now, as a special case, if the instant of time t is one where rolling has commenced, then see, this equation is true irrespective of whether this is a rolling state or not, right? This will be true for any instant of time t. But if this also is a rolling state, then I can write omega as VCM by R. Then I can write omega as VCM by R, and I can calculate VCM directly. I can calculate VCM at an instant when rolling started right away by using conservation of angular momentum. Are you all right with this or not? So if somebody says calculate the velocity of the center of mass at an instant when rolling starts, you can avoid all those equations that I wrote. VCM is V naught minus mu gt, and then I equate VCM, and then I calculate T, and then I calculate VCM. You can avoid all of that. You can right away start by writing the conservation law and plug in omega equal to VCM by R, and this equation would give you VCM straight away. Is that a fair proposition? Right? Okay. Now, see, we started with pure translation. V naught for all particles. Initially they were slipping because there is relative motion between the point of contact and the surface. So initially it started to slip. When it started to slip, eventually VCM decreased, omega increased, and rolling conditions were produced. VCM, omega, and if this was a state of pure rolling, then VCM equal to R omega at this instant of time, right? This is pure rolling. And all along, from this state to that state, friction in this particular case, acted backwards. And then, beyond this state, what do you think friction would do? Will it act to the left or will it act to the right? Beyond this state, see, until this state, friction acted leftwards, continuously killing VCM and enhancing omega R. And then beyond this state, what would be the role of friction? What would be the action of friction beyond the state? First, whether it's going to act to the left or it's going to act to the right. Rolling starts here. Suppose it acts to the left. Suppose it still acts to the left. First of all, beyond this state, whether this frictional force would be static or kinetic. Static. Why? Because if there is no relative motion between the body and the point of contact, then frictional force in rolling conditions will always be static. Right? So it will always be less than mu mg. Right? Now if it's static friction, whether it's going to act to the left or it's going to act to the right. Assume that it acts to the left. Now if it acts to, and this is static friction, its value would be less than maximum static, less than mu mg. So you do not know what value it has. But then you you certainly know that it could have any value from 0 to mu mg. Now, if it acts to the left, then it's going to kill VCM. It's going to increase omega. That means VCM equal to R omega will get disturbed, because in this state, VCM is R omega. If VCM will decrease and omega will increase, then VCM will no longer be equal to R omega. So, if friction force acts to the left, it will disturb rolling. It acted all the way so that it could produce rolling. Why would it now on its own go ahead and disturb rolling? Right? So, it can't act to the left. So, let's assume that it acts to the right. Say it acts to the right. Now, if it acts to the right, it will accelerate the body to the right. VCM will increase. VCM will increase if it acts to the right. And this F will produce an anti-clockwise torque about the center of mass. And therefore, it will produce an anti-clockwise alpha that will kill omega. If VCM increases and omega decreases, then VCM equal to R omega will again get disturbed. That means rolling conditions will then get disrupted. So, it can't act to the right. It's a friend of rolling. It's never going to disturb rolling. If it can't act to the left, if it can't act to the right, it will not act upwards or downwards, because friction can't act upwards or downwards. It will always act tangential to the surface. So, then friction says, all right, kid, you've grown up enough, roll on. It will not act. Static friction, after all, F equal to 0 is also static friction, isn't it? So, in this particular case, once it has done its job and it finds that this VCM retained, this omega retained, the body would roll on thou deep and dark blue ocean. It will never stop, right? Theoretically, it will continue to roll on forever. With the VCM being maintained, the omega being also maintained. Assume that there are no other forces acting on the rigid body. This surface is horizontal. Yes or no? Now, between this state and this state, friction had to play a little ugly. Acted leftwards, there was rubbing between the body and the surface. So, the kinetic energy of the body got killed. The total kinetic energy, half mv squared plus half ICM omega squared, decreased. Right? But beyond rolling, there is no rubbing between the body and the surface. There is no rubbing between the body and the surface. So, the VCM will be maintained, the omega would be maintained, and therefore, beyond this point, the total kinetic energy would be maintained, because the same VCM, the same omega, kinetic energy will be retained all along beyond this point, beyond the rolling state. But up to the rolling state, in this case, friction has played the devil's role in terms of decreasing the total kinetic energy. It had to do so that it could eventually promote rolling. Are you all there with me on this? Now, let me look at another possibility. This was one where I started to translate the rigid body, and eventually rolling conditions commenced for a disk. It took time t equal to v naught by 3 mu g for rolling to commence, right? Let me set up a rigid body in pure rotation. Means it has no VCM, but it has only omega naught. It has only omega naught, and then see what transpires. Pure rotation means no VCM. Pure rotation means no VCM. This is spinning, so to say. It's spinning about the center of mass. It's spinning about the center of mass. Clear? And again, like before, mu be the coefficient of static friction, mu mg approximately equal to kinetic friction, right? Look at the point of contact when you set it up in a pure spin, pure rotation. This point has a leftward velocity r omega naught. Yes or no? It has a leftward velocity r omega naught. So if it has a leftward velocity r omega naught, then the writing is on the wall. Frictional force would act to the right. And it would be kinetic in nature. Why? Because there is rubbing. Right? Kinetic friction means approximately maximum static means mu mg. And therefore, the center of mass would witness an acceleration mu g. Would witness an acceleration mu g. Very clearly, the center of mass has zero initial velocity and it has a rightward acceleration. Therefore, the velocity of the center of mass would increase with time. Right. So, at an instant of time t, you would expect VCM to be initial VCM, which is 0 plus AT. A is mu g. So, VCM increases. Now, this frictional force produces an anti-clockwise torque about the center of mass. Yes or no? Right? Torque about the center of mass is mu mg into r anti-clockwise. Torque about the center of mass is mu mg into r anti-clockwise. Now, this anti-clockwise torque will produce an anti-clockwise alpha, right? So, it's going to produce an anti-clockwise alpha. And I'm perfectly eligible to apply tau equal to I alpha above the center of mass. So, this alpha is going to be tau about the center of mass divided by I about the center of mass. Right? So, this is going to become again mu mg into r divided by half mr squared, which is like 2 mu g by r, which is like a 2 mu g by r. Now, this alpha opposes omega. So, this is like angular retardation. So, t seconds later, the omega that you would witness on the rigid body would be the initial omega minus alpha t. Which means now omega is decreasing with time, VCM is increasing with time. So, what's friction doing? In this case, the weaker entity was translation, and translation gets promoted. Omega was the stronger entity here, and omega was being killed, right? Omega was being killed. You would then expect at some instant of time VCM to become equal to R omega, and that would mark commencement of rolling. So, at T naught, where VCM becomes equal to R omega, mu g T naught is R omega. R omega, as you can see here, is omega naught R minus 2 mu g T naught. And that tells us that T naught must be omega R divided by 3 mu g. That's the time. Again, if mu is high, the time taken for commencement of rolling is. So once again, whether you start from pure translation or you start from pure rotation, eventually it will all culminate into pure rolling. And friction is instrumental and responsible towards production of pure rolling conditions. Pure rolling conditions. Yes or no? And beyond this point, beyond rolling, you'll have the same state like I discussed. VCM will be retained, omega would be retained, and so on. There would be loss of kinetic energy from here to there, but then when it's rolling, frictional force would become static in character. It will be less than. And also, between this state and this state, irrespective, I can still apply conservation of angular momentum about the point of contact, right? So if I have to apply conservation of angular momentum about the point of contact, whether this is pure rolling state or not, right? Torque about the point of contact is still zero in both these states. From here to here, it has been zero all the way. And therefore, L about the point of contact can be conserved. Angular momentum about the point of contact can be conserved between any two states. So in the initial state, this is angular momentum about the point of mvcm into r, which is 0 here because vcm is 0, right? mvcm into r is 0. Why? Because vcm is 0 plus icm omega naught plus icm naught. So initial angular momentum is icm omega naught. And in this state, the angular momentum because of pure rotation is icm omega plus mvcm into r. mvcm into r clockwise. And as a special case, if this happens to be a state of pure rolling, I can replace omega by vcm by r and calculate vcm directly without going through all of what we did a little while ago. We can bypass those calculations, and just by using conservation of angular momentum, I can calculate vcm at an instant when rolling starts by simply plugging in omega equal to vcm by. Yes or no? Huh? There is a cockroach. Oh my God, we'll have to call the forest authorities to take care of that cockroach. Hey, Akbar, switch off for ROE cockroach. Now, let's look at what Harbhajan Singh does. Reverse spin. Reverse spin means the Bhaji effect. It's like forward velocity of the center of mass, but backward spin, omega naught. So, center of mass is the rightward velocity, but the whole thing is rotating like this. That's reverse spin. That's reverse spin. Yes or no? Now, let's look at the point of contact. Let's look at the point of contact. Because of pure translation, it will have a velocity v naught to the right. Now, because of pure rotation about the center of mass, it will have r omega naught also to the right. Yes or no? That's the velocity of the point of contact. Clear? Which means this point has a rightward velocity at time t equal to 0. The surface is at rest. The surface is at rest, and therefore, frictional force would be kinetic in nature, approximately equal to maximum static, and would act leftward. And would act leftward. And would be of value mu mg. Would be of value mu mg. Now, in this case, both the velocity of the center of mass and omega are having some charbi, some flesh. Point of contact having a velocity to the right is not supported by friction. It acts to the left. Eventually, it wants to kill both. So, it would want to kill V naught as well as omega naught. See, this F acting leftward will produce a leftward A equal to mu G, and it would also produce a clockwise alpha. It will also produce a clockwise alpha, and it will kill. Both are getting killed. You know what I'm saying? This F acting backwards will produce an alpha like this, and this alpha would kill this omega naught. So both omega naught and V naught are being suppressed by friction here. Now, both the velocity of the center of mass and omega are coming closer and closer to 0. It's like one or the other possibility. At an instant of time t, in any case, VCM becomes equal to V naught minus mu. And the omega would be omega naught minus alpha t, where what's alpha? Alpha we've computed is 2 mu g by r, retardation, right? Like we've done earlier, 2 mu g by r into t, that's omega. Now, three possibilities for this, right? Possibility 1. VCM becomes 0, but omega not 0. VCM becomes 0, but omega is not. That means the body enters a state of pure translation, pure rotation, because VCM is 0 and omega is not 0. A state of pure rotation is obtained, which is like one of the earlier cases that I have discussed. From pure rotation to pure rolling will be another journey, would be yet another journey, and that part has been discussed, right? This is one possibility. Possibility 2. VCM is 0, but omega is not. VCM is not 0, but omega is. VCM is not 0, but omega is 0. That means it enters a pure translation regime. It enters a pure translation regime. And again, from pure translation to pure rotation, there would be pure roll. From pure translation to pure rolling would be yet another phase, right? The two possibilities. The third possibility is both become 0 simultaneously. both become 0 simultaneously. VCM is 0, omega is, and if both become 0 simultaneously, then friction will not act. That means now the body has come to rest till eternity. I mean, if a body has permanently come to rest, if you put it on the surface, friction will not unnecessarily kick it and lick it, right? It will not get into that hassle. It will stay at rest forever. It will stay at rest forever. You know what I'm saying? Which means at the same T, omega and VCM becoming 0. At the same T, omega and VCM becoming 0. That's the third case. That's the third case, right? So VCM becomes 0 at an instant of time T, given by V naught by mu G. At an instant of time T, given by V naught by mu G, VCM becomes 0, right? And at an instant of time T, omega becomes 0. Omega becomes 0 at T equal to R omega naught by 2 mu G. And if it's the same instant, if it's the same instant, then R omega naught by 2 mu G. At the same instant T, VCM and omega becoming 0. That means this must be the condition. This must be the condition to be met so that the body eventually comes to rest forever. This must be the condition so that when you set it in a state of reverse spin, the body stops right in front of the batsman. Right? You know what I'm saying? This, of course, I could have arrived at this condition so that the body finally comes to rest. Could have arrived at it without writing these equations. How? Let's say if it actually comes to rest finally, which will not happen in state 1 and state 2, because state 1 and state 2 would eventually migrate into pure rolling, right? And then it will roll on forever. So state 3, when VCM is 0 and at the same instant omega is 0. At the same instant omega is 0. Whatever it is. The angular momentum about the point of contact is to conserve. Yes or no? So now, if this is some state that actually occurs during the motion, if this is some state that is achieved during the motion, if such are the values of V naught and omega naught, that this state actually is achieved sometime, then do you realize that this state would give us an insight into the total angular momentum initially. Why? Because see, I know VCM and omega being 0, that means angular momentum above the point of contact is 0 here and must have been 0 there. Yes or no? So L above the point of contact, as can be judged from this state, if it at all occurs, is 0. And therefore the angular momentum above the point of contact here must be 0, right? Which is like, look, I take clockwise positive, anti-clockwise negative. So mv naught into our clockwise angular momentum. And this omega will give me anti-clockwise angular momentum. So minus ICM omega naught. This will be this. Then if you plug in ICM equal to half mr squared, it will give you the condition, the relationship between V naught and omega naught, so that the body comes to rest permanently. Right? You there with me on this? Right? And this is the same as this condition. If you cross multiply, you will get the same condition basically. Now what I'll do is, I'll use sheet 1 as an illustration sheet. So I'll solve some stuff for you so that you get an initial kickstart and then you start to roll. Okay? Let me discuss some stuff with you. We will write down the physics involved in every problem. Leave it at that. Some important ideas would be directly made available to you by means of these problems. All right. Hoop means it's like a ring. Hoop means it's a ring. That means its ICM is mr square. Its ICM is mr square. So we have a circular wooden hoop of mass m and radius r resting on a frictionless surface. This is a frictionless surface. A bullet, also of mass m, moving with a velocity v, strikes the hoop at this point and gets embedded in it. Find the angular velocity with which the system rotates. Find the angular velocity with which the system rotates. All right. Let's look into the physics of the problem. Look, when this mass and this hoop are looked upon as one system, one family, then what this is bringing to the system is forward linear momentum, right? So once it becomes integral with the family, the center of mass start to have a velocity forward. So one effect because of this impact is that the center of mass of the hoop alone, will have a rightward velocity. That's one effect. Okay. That means right after impact, velocity of the center of mass is VCM. Yes or no? Not only that, look, as far as the center of mass is concerned, look at this. When it just strikes the bottom point with a velocity v, it strikes with a velocity v initially, just before impact, it has a velocity v. That means what it's bringing to the system, is mv into r, angular momentum about the center of mass, anti-clockwise. It's bringing an anti-clockwise angular momentum to the system, and therefore because of this impact you would expect an omega in this sense to develop on the rigid body, Now, one thing, if you look at the bullet and the hoop as one system, one unit, then there are no horizontal forces externally acting on the system. The bullet exerts a force on this, and this exerts a force on the bullet. But other than that, so these for the family are internal forces. So no net external force in the horizontal direction for the bullet plus hoop system. No external forces horizontal. As far as the bullet is concerned, well, when it becomes integral with the hoop at this point, then it will share the same velocity as that of the hoop at this instant. Now, what's the velocity of this point? Because velocity of the hoop at this point right after impact. Because of pure translation, it's going to be VCM because of pure translation, and because of pure rotation, it's going to have a tangential velocity r omega. So this point right after impact has a velocity VCM plus r omega, VCM plus r omega. Now the bullet gets embedded at this point, so the bullet will also have the same velocity VCM plus r omega, yes or no? So the bullet will also share the same velocity VCM plus r omega, VCM plus r omega. Now let's start by applying the relevant principle. First of all, the linear momentum for the bullet plus the hoop horizontally must be preserved. What did we start with? We started with the hoop at rest and the bullet having a horizontal velocity. So between the two, they had a total linear momentum mv to begin with. Total linear momentum mv to begin with. And right after impact, this is right after impact, the hoop had a linear momentum m into VCM. The VCM is a representative of the total linear momentum for a collection of particles. For the hoop alone, it's mVCM. Now, for the bullet, which has become integral with the hoop, the linear momentum horizontally is going to be m into VCM plus r omega. M into VCM plus r omega, yes or no, right? Clear? I told you when we start with conservation of angular momentum, if there are particles interacting with each other and there are no horizontal forces, if there are no external forces acting, external torques acting, there are no external torques acting about a point, about any point, then the angular momentum of the system about any point will be conserved. In this case, for example, for the hoop plus the bullet, the hoop has no angular momentum about this point. The hoop has no angular momentum about this point because it's at rest. The bullet has its line of action of the velocity passing through this point. So the bullet also has no angular momentum about this point. Yes or no? About the point of impact. Means, right just before impact, the angular momentum about the point of impact must have been, yes or no? Angular momentum about the point of impact is 0 just before the impact, right? For the bullet plus the hoop. If you fail to register this, please ask me, I'll explain again. Is there anyone who's kind of lost with this thought? No? Now, so it must be 0 right after impact also. Now, right after impact, the bullet once again contributes to no angular momentum about this point because its line of action of the velocity passes through this point. As far as the hoop is concerned, it has a mVCM into r clockwise and ICM into omega anti-clockwise. So its angular momentum about the point of impact finally for the bullet plus the hoop, bullet is 0 plus the hoop is mVCM into r clockwise minus ICM omega anti-clockwise. Conservation of angular momentum, conservation of linear momentum. Have we exhausted the conservation laws here? Right? And what are we expected to calculate here? Calculate the omega. Omega is what is required of the. Now, what are the two unknowns? VCM and omega. Two equations and two unknowns. And you can solve for omega from these two. This is the physics. The rest is algebra. The rest is algebra solving for omega. And just out of academic interest, let me write the angular momentum about the center of mass. It's just going to be, it still will give you the same final omega. I mean, if I choose to write angular momentum about the center of mass, well, to begin with, what was the angular momentum of the system about the center of mass? Hoop was 0 because it was at rest. For the bullet, it was mv into r anticlockwise. mv into r anticlockwise for the bullet just before the impact. And this was the total anticlockwise angular momentum before the impact. Just after the impact, the anticlockwise angular momentum. Well, the bullet, I am taking anticlockwise positive, let's say, and clockwise negative. So just after impact, the bullet alone has m into VCM plus r omega into r anticlockwise, right? The bullet alone. R plus. Now the hoop about the center of mass will be simply ICM omega anticlockwise. Would be ICM omega anticlockwise about the center of mass. So, equations 1, 2 and 3 essentially, whether you use 1 and 2 or you use 1 and 3, you will get the same value. You will get the same value, whatever you feel convenient. You don't use 2 and 3. You don't use 2 and 3. Both refer to the same physical principle rewritten. One is one physical principle, 2 and 3 essentially the same physical principle written algebraically differently. That's all. Are you there with me on this? So either use 1 and 2 or use 1 and 3 to solve for omega. You arrive at the same value of omega. So do you understand the physics involved in the problem? Okay. There is a stick of length L and mass m lying on a frictionless horizontal surface. This board is now looked upon as a horizontal frictionless surface, right? And it's free to move anyways. This is the center of the rod, that is the center of mass of the rod for that matter. A ball of mass m moving with a velocity v collides elastically with it, means perfectly elastically with the rod, and actually, elastically with the stick. What must be the mass of the ball so that it comes to rest after collision? What must be the mass of the rod so that it comes to rest right after perfectly elastic collision occurring at a distance d from the center of mass? So this is the state just before impact. This is the state. What is it bringing to the system? What is the particle bringing to the system? Horizontal linear momentum. So right after impact, the stick for sure will develop a VCM, right? Not only that, because of this impact, this will exert on the stick a torque like this about the center of mass. So the stick will develop an omega like this after the collision, right? Not only that, the mass right after collision This is just after collision. The mass m right after collision has a velocity v equal to 0 right after collision. Right after collision, the mass is known to have a velocity v equal to 0. We are then attempting to calculate the value of the mass m so that all of this could occur in the event of a perfectly elastic collision. Look, first things first, no external horizontal forces in this direction acting on the particle plus the stick. Particle plus the stick, no external forces. They exert forces on each other, they exert impulsive forces on each other that cancel off in pairs. So, nothing external. So, then it makes us eligible to apply the conservation of linear momentum for the particle plus the stick. For the particle plus the stick, we become eligible to apply the conservation of linear momentum. So, what is it that we apply with, that we have originally? Conservation of linear momentum. MV is what we started with, right? And finally, it was capital M into VCM, capital M into VCM, because this stayed with no linear momentum after impact, right? So, capital M into VCM. That's principle number 1. Now, between the particle and the, they exert equal and opposite forces on each other during the collision period. So then the R cross F about any point for the particle plus stick would be 0. The net torque about any point, because see, the particle exerts on the stick a force in this direction, the stick exerts an equal and opposite force on the particle in this direction. Then take any other point about this point, the torque because of this force and the torque because of an opposite force would be 0. So the net torque acting on the particle plus the stick about any point is 0. Right? Which means about any point, we should be geared to apply the conservation of angular momentum. So I can either apply conservation of two convenient points, to either apply conservation of angular momentum about the point of impact or the center of mass, or you can apply conservation of angular momentum about Scotland. Does not matter, right? It will still be 0, right? You know what I'm saying? So then, let's apply conservation of angular momentum, say about center of mass. Conservation of angular momentum about the center of mass for the particle plus the stick, in view of the fact that the torque on the particle plus the stick system about the center of mass of the rod or about any other point is, right? So, angular momentum about, let's say, the center of mass is constant. What's the angular momentum initially about the center of mass? This has no angular momentum. So, mv into d anti-clockwise. mv into d, this is v is like this. So, mv into d anti-clockwise. Initially. And then finally, this comes to rest right after collision. So, it produces no angular momentum about any point. So, also for the center of mass. So, angular momentum about the center of mass of the stick produced by the particle is 0. But the stick alone about its center of mass would be, angular momentum about the center of mass in general motion would be ICM omega. ICM omega about the center of mass alone. So, ICM is 1/12 ml square into omega. 1/12 ml square into omega. Capital M, this is capital M, L squared into omega. EV anti-clockwise, because see, this omega is anti-clockwise, right? Realize that what are the unknowns here? What are we seeking here? Small m. So small m is an unknown. VCM and omega, those are unknowns because we were only pretentious about VCM and omega. No clue what they are really. So two equations, which means there is a void to be filled. There is some physical principle yet to be applied. In these two equations, we have nowhere factored in the fact that the collision is perfectly elastic. Collision is perfectly elastic has not been represented mathematically yet, and that will be our concluding remark on the physics of the problem. You know what I'm saying? Now, look, this point P on the rod, which is where the impact takes place. This point P on the rod, where the impact takes place, had zero velocity initially before the impact. And this point P on the rod right after impact is going to be, if I superimpose pure translation with pure rotation, this point P will have a VCM plus minus plus omega d to the right. Yes or no? See? This is VCM. This is omega. So because of pure translation, it's VCM. And then imagine it to be in a state of pure rotation about the center of mass. So it will have a omega d to the right. So VCM plus omega d just after impact. Just after impact. I hope you understand this. So the point P right after impact has VCM plus omega d, the point where the impact takes place. Now look, if somebody tells you that the collision is perfectly elastic, one of the things that you can do is you can write a complicated kinetic energy equation. Total initial kinetic energy is total final kinetic energy. The kinetic energy equation has a quadratic nature. It's a little more complicated to solve. And therefore, a superior substitute for that, for a perfectly elastic collision representation, is by saying E equal to 1. Right? E is relative velocity of separation divided by relative velocity of approach, where one of the particles is the small m, the other particle is the point P where the impact occurs. So between the point P where the impact occurs and this particle m, I'll apply relative velocity of separation divided by relative velocity of approach. Relative velocity of separation means, let's say in the numerator I take the particle m minus the point P. Then in the denominator I'll take the particle P minus the point P minus the particle M. That's how I'm going to take, right? So then relative velocity E is 1 means relative velocity of separation, say 0 minus VCM plus omega d, right? Relative velocity of separation divided by relative velocity of approach. This was approach. In this, what am I going to take? I'm going to take the particle P, the point P minus V. Point P has 0 velocity minus V. That's 1. So it gives me V equal to VCM plus omega t. Right? Now, this VCM, I can, now it's all algebra. This VCM, for example, I can write as MV by capital M. This omega, I can write as 12 MVD by capital ML squared. Yes or no? This omega, I can write as 12 MVD divided by ML squared. This omega into D, omega D squared. Yes or no? Now very clearly, this V, this V, this V would get cancelled and small m would be available for calculation. Are you fine with this? Did you get me? Let me look at D. C, sorry, C. Now one quick thing. You know what an impulsive force is? A force that acts for a short time. That acts for a very short time, that's an impulsive force. Right? So, if there is a rigid body, and let's say initially it has an omega naught and it has its center of mass has a velocity v naught. Its center of mass has a velocity v naught. And in a state of general motion, as you can see, the important thing is, if there is that means when somebody says a body is tapped, tap means it's not a force acting all the way, it's a force acting for a short time. That's tapping, right? That's tapping. Say, for example, there is a force F acting like this. And for convenience, let's say this force is parallel to V naught, for example, right? And it acts for a short time, delta t. It's an impulsive force acting for a short time, delta t. Now, impulse of a force does what? Produces change in linear momentum. Impulse of a force will produce change in linear momentum. And the linear momentum would get reflected in the change of velocity of the center of mass. So, right after the impulse, this is an impulse acting for a short time, delta t. Right after the impulse, say VCM becomes VCM becomes VCM. Okay. Clear? So then if this F, now the impulse in the direction of this velocity is what? F into delta t, F into delta t, that's the impulse. And that must be change in linear momentum. So change in linear momentum is m into VCM minus V naught in this case. The change in linear momentum in the direction of the impulse, the change in linear momentum in the direction of the impulse, right? Final linear momentum in the direction of the impulse minus initial linear momentum in the direction of the impulse. That's the impulse. Not only that, there is a torque acting about the center of mass for a short time, delta t, right? Because of this force acting here, in this case, say this distance is d. Then for a short time, delta t, there is a torque acting about the center of mass in this case. Yes or no? There is a torque acting about the center of mass, but for a short time. So there is an impulse of a torque. It's called angular impulse. This is called linear impulse. This is called linear impulse. And the torque acting for a short time will be angular impulse, right? So then in this case, what's the torque acting? The torque acting is F into d about the center of mass. This is angular impulse. Whereas linear impulse produces change in linear momentum Angular impulse produces change in angular momentum. So, angular impulse about the center of mass is going to be F into D into delta T. The torque into delta T, force into delta T is linear impulse, torque into delta T is angular impulse. So, this is angular impulse about the center of mass. This is angular impulse about the center of mass. Because I have taken the torque about the center of mass. And that must be change in angular momentum about the center of mass. So, if the initial omega was omega naught, and just after the impulse, the omega became omega, then the final angular momentum above the center of mass is going to be ICM omega. The initial angular momentum above the center of mass is going to be ICM omega naught. So, change in angular momentum is going to be ICM into omega minus omega naught. Linear impulse produces change in linear momentum. Angular impulse will produce change in angular momentum to keep things simple. And now, if you want to, this delta T is not of interest to you, you can divide this by this and dispense away the delta T and stuff, right? Now, let's look at the next problem. C. So, this rod initially at rest on a horizontal frictionless surface, right? And it's tapped at this end by a force F. That means there is an impulse of a force. There is an impulse of a force. That means right after this force is withdrawn, you would find the center of mass having a rightward velocity. Because a change in linear momentum in the direction of the impulse is proposed. If acting in this direction, right after the impulse, you would expect the center of mass to develop a velocity VCM to the right, to develop a velocity VCM to the right. Clear? Let's express that mathematically. Say this force F acts for a short time delta T, then the impulse, linear impulse, so to say, is going to be F into delta T. That must be M into change in velocity VCM. That's a change in linear momentum. How about it? How about it? This force produces a torque F into L by 2 about the center of mass. It produces a torque F into L by 2 about the center of mass, clockwise torque. It produces a clockwise torque. And this torque F into L by 2 acts for a short time delta T. So, torque into delta T would give me angular impulse. So, angular impulse about the center of mass is change in angular momentum. Initial angular momentum above the center of mass 0. Therefore, you would expect an omega to develop right after the impulse. Right after the impulse, you'll expect an omega. So then, final angular momentum about the center of mass is going to be ICM omega. Initial angular momentum about the center of mass is ICM for the rod is about the center of mass 112 ml square into omega. So angular impulse would be change in angular momentum. This is angular impulse about the center of mass. This is change in angular momentum. Right? And now, what I could do is realize that this F into delta T could be written as capital M into VCM. This F into delta T I can write as capital M into VCM. F into delta T is capital M into VCM, and then by 2 into L. Yes or no? Into L must be 112 ml squared omega. Yes or no? So this M will get cancelled. This M will get cancelled. 1L cancelled here. 1L cancelled here. This gives me VCM equals L omega by 6. Right? Now, look at what's required in the problem. How far does the center of mass translate? That means the distance covered by the center of mass. Look, the center of mass will keep getting reoriented. It will have VCM like this, but it will also rotate. So, it will have a trajectory. It will have a trajectory. I want to be able to compute the distance traveled by the center of mass. But VCM will remain the same for the center of mass. VCM will not change. VCM will remain the same. It will move as well as get reoriented. VCM will continuously move like this, and the rod will continuously get reoriented. Right? Now, in one full revolution of the rod, what's the time it takes for one full revolution? Well, revolutions are produced by omega. Revolutions are produced by omega. So, what's the time it takes for a full revolution? 2 pi by omega is the time it will take for a revolution, even though the center of mass would have drifted rightwards. Time it takes to get restored to its vertical state, original vertical state would be 2 pi by omega, even though the center of mass would have moved rightwards in this time. But the rod would have got back to its original orientation in these many seconds, 2 pi by omega, right? Distance traveled by the center of mass in this time? Well, center of mass has a constant velocity, so VCM into T. Right? Where T I can write as 2 pi by omega. And VCM by omega is L by 6. As you can see from this equation, VCM by omega is L by 6. So, L by 6 into 2, which is pi L by 3 is the distance covered by the center of mass by the time the original orientation is restored, right, in one full rotation. This is idea driven. You all understood this concept. Now, one more thing which I want to tell you is, work done via torque See, this is a rigid body and there is a torque tau acting on it. There is a torque tau acting on it. Huh. And this torque could have been produced in many ways. For example, this torque tau could have been produced by a force F acting like this. This torque could have been produced by a force F acting like this. So that this torque would be like a F into R. This torque about the center of mass would be F into R. Now, this is the point of application P. This is the point of application P. In a short time dt, this point P would have moved to a very nearby point P prime. Because of the torque, it would have moved to a nearby point P prime, where this angle would have been d theta. The body would have got rotated by an amount d theta in this short time. And this PP prime, the arc PP prime, would have been RD theta. The arc PP prime would have been RD theta, yes or no? Now, just to give you an enlarged view of the whole thing, this is PP prime, which is like a RD theta. Now, realistically, this is very, very small. This is very, very small. So, almost like a straight line. This is almost like a straight line. So, we can always almost approximate it to a PP prime like this, horizontally, RD theta. Almost like this. Almost like this. This d theta is very small. This arc is very small. This is almost a straight line. I mean, PP prime would have hardly moved downwards. It would have been only practically a horizontal displacement. Yes or no? So, and the force F that produced the torque tau was acting this way. So, what's the work done by this force? F into RD theta. So, the work done by this force is F into RD theta. But F into R was the torque about the center of mass. So, let's see, torque about the center of mass into d theta. So, the total work done would have been sum total of all this, integral this. Let's say theta changes from 0 to some theta naught. This is the work done by a torque. This is the work done by tau d theta, sum of all of this. Theta, let's say, runs from 0 to some theta naught. Clear? Now, just to illustrate this, look at problem E. Look at problem E. And if torque is constant, see, I said tau cm d theta. If torque is constant, it will come out. It will be tau cm integral d theta. Integral d theta is the total theta rotated. Is the total theta rotated. Right? In case of a constant torque, if the torque is constant, then the work done by the torque is tau cm into the total angle theta rotated. Right? Yeah. Look at E, problem E. So, we have this body initially set into a spin with an angular velocity omega naught, right? And it's in contact with the two surfaces, this vertical surface and this horizontal surface, and coefficient of friction is mu on both these surfaces, right? If you want to find the time it takes for it to come to rest, that means omega becomes 0. That's what we want to find. Or is it like, what is it that we, okay, how many turns does it take to come to rest? We want to find the number of turns that it's going to rotate before it comes to, okay. And look, first, write down the free body diagram, alright. There is going to be a normal reaction from this, say N1. This point, because of omega naught, this point has a rightward velocity. So frictional force would be kinetic in nature, approximately maximum static. So mu N1 leftwards, frictional force at this point acting on the spinning body is going to be mu N1 leftwards. Right? Now, there is normal reaction from this surface, call it N2. Call it N2. This point, because of this omega, has a downward velocity. This point has a downward velocity. Yes or no? R omega. So frictional force at this point on the rigid body will act upwards and would be kinetic in nature, approximately equal to mu N2. Mu N2. Upwards. Yes or no? Now, in each case, the center of mass is staying put here. The omega is getting killed, but the center of mass is staying put. That means the acceleration of the center of mass is 0. Means in the horizontal direction and in the vertical direction, net of all forces must be 0. Yes or no? So in the horizontal direction, what are the forces? N2 and mu N1. So N2 must be mu N1 in view of translation in the horizontal direction. N2 must be mu N1. That's the translation horizontally, right? Okay. In the vertical direction, again, net of all forces must be 0. No acceleration in the vertical direction. So mu N2 must be equal to N1. Mu N2 must be equal to, I'm sorry, there is also mg. There is also mg acting downwards. So mu N2 must be, mu N2 plus N1 must be, see, mu N2 plus N1 must be, right? Now this N2 I write as mu N1. So I get N1 equals mg by 1 plus mu squared, and N2 is mu N1. N2 and N1 are known then? N2 and N1 are known? Now, look, if the body rotates in the direction of the torque, in the sense of the torque, then the work done by the torque is positive. But if it rotates opposite to the direction of the torque, then the work done by the torque will be negative. Tau d theta. If d theta is in the direction of the torque, in the sense of the torque, work done would be positive. If it's opposite to the torque, work done by the torque would be negative. Now, look, what's the net torque? What's the net torque about the center of mass? Well, there is mu n1. This is mu n1 into r. Is a clockwise torque about the center of mass, mu n1 into r. Mu n1 into r is a clockwise torque about the center of mass, yes or no? Clockwise torque, right? And mu n2 into r is also a clockwise torque about the center of mass. Yes or no? It's a constant torque. It's a constant torque. The body is rotating in the anti-clockwise sense, whereas the torque is in the clockwise sense. Torque is clockwise, the rotation is anti-clockwise. Say, if it rotates n revolutions, then what's the total angle rotated in n revolutions? 2 pi n. 2 pi n, yes or no? Say n revolutions, then the theta rotated in the anti-clockwise sense is going to be 2 pi n. Is going to be 2 pi n anti-clockwise sense. So then, tau is clockwise, the total theta rotated is anti-clockwise. So the work done by this torque would be negative. So what's the work done by the torque? Is minus mu n1 plus mu n1 plus n2 into r into the theta rotated, which is 2 pi n. Negative work done by the torque. What's the initial kinetic energy of the spinning body? Half ICM omega naught squared. That's the initial kinetic energy. What's the final kinetic energy? 0. Final kinetic energy is 0 because it's coming to rest. Right? Apply work energy theorem. Work done by the torque is going to be change in kinetic energy. So then all that you need to do is work done by tau cm is final kinetic energy 0 minus initial kinetic energy half ICM omega naught squared. So plug in W tau cm from this, n1 and n2 are known, and calculate small n. Calculate small n. Got me? Is that all right? So well, some ideas have been illustrated today. I want to take an extra class on Saturday. Is it that we stopped on sheet 1? E. All right. So we have this fixed bigger sphere and a smaller sphere that rolls down the outer surface of this sphere. We want to be able to find the omega for the smaller sphere at an instant when it's on the verge of losing contact with the bigger sphere, right? Now, few basic things about the motion of the smaller sphere. One, the fact that it rolls down means the frictional force between the smaller sphere and the larger sphere is static in character. F is F static. F static means there is no rubbing between the smaller sphere and the bigger sphere, which means there is no dissipation of energy, which means we are perfectly eligible to apply conservation of energy. The loss of potential energy must be gain of kinetic energy, and kinetic energy at this point would be constituted out of 1, kinetic energy of translation, 2, kinetic energy of rotation, right? So then, at this juncture, the smaller sphere has its center of mass having a velocity v, and it has an angular speed omega at this juncture, right? Realize that this is small r, and this distance Cp prime, distance from C to P is r plus small r, right? R plus small r. Yes or no? Now, the loss of elevation is this. Which is this. This total length is r plus r, and this is r plus small r cos theta, right? So the loss of elevation Pm will lead to loss of potential energy mg r plus small r into 1 minus cos theta. Yes or no? R plus small r minus r plus small r cos theta is Pm. Yes or no? Do you all understand this? And what does it get converted to? When it arrives at P prime, it gets converted into kinetic energy of translation plus kinetic energy of rotation. So, which is like the total kinetic energy of the rigid body, half m v squared plus half ICM for a sphere is 2/5 mr squared. Half ICM omega squared. So that's the energy implication, and we could apply energy because it's rolling down and friction is static in character. There is no loss of energy. Now, the center of the smaller sphere, it negotiates a circular trajectory of radius r plus small r. Yes or no? P moves along the arc of this circle centered at C and having radius r plus small r, right? At any point of time, therefore, P would have a centripetal force requirement. Realize that at this point of interest, the centripetal force requirement is going to be mv squared by r plus small r. This is the requirement. This is the centripetal force requirement at this juncture. And if you look at the free body diagram of the smaller sphere, then it's subject to mg downwards and normal reaction n like this. Yes or no? These are the two forces acting. Now, if this represents the instant of loss of contact, then that's characterized by n equal to 0, right? N equal to 0 would characterize loss of contact. So, n equal to 0 at this instant would mean that this is the instant of loss of contact, and therefore the centripetal force requirement is met by the component of mg along PC. component of mg along PC. So which is like mg cos theta, which is like mg cos theta. Now, realize that when it goes from P to P prime, it's been rolling all the way. It's been rolling all the way. So, at this point, it has a linear velocity v and an angular velocity omega, right? The radius of this is small r. And therefore, for rolling requirements, v must be small r omega. V must be small r omega. This is the sum total of all the physics required by the problem. And all that you need to do is solve for omega. Solve for omega. The answer seemed to have a log. It must be 10. It must be 10. It's not log, it must be 10g. The log actually must be 10g. So we have this cube which slides down with a constant velocity. Slides down with a constant velocity. Constant velocity means its acceleration must be 0 in all directions, in any direction. That means net of all forces in any given direction must algebraically add up to 0. Very clearly, along a direction parallel to the plane, there are only two forces acting, mg sine theta and f, and they must balance each other for maintaining constant velocity, right? So first things first, f must be mg sine theta. Right? Now, realize that this f about the center of the cube, this f about the center of the cube will produce a torque F into A by 2 in this sense. Yes or no? Anti-clockwise sense. F into A by 2 in the anti-clockwise sense. Now, mg cos theta or mg sin theta produce no torque about this point, right? So, if left to friction alone, it will tumble the cube down. It will topple the cube down, right? And this is where the normal reaction comes into play. It says that, well, if normal reaction conventionally as it is, if it passed through the center, then it wouldn't have an option of creating a restoring torque to counter the torque of F. Therefore, N compromises with its position. It says, all right, my line of action along this conventional direction is inappropriate in as far as maintaining rotational equilibrium is concerned. It's time that I acted in a manner so that I could produce a clockwise torque to counter the anti-clockwise torque of F and thereby maintaining rotational equilibrium. And therefore, the line of action of N shifts leftwards. The line of action of N shifts leftwards, let's say by an amount X. Let's say by an amount X. So that the torque of N about O must be equal to torque of F about O, maintaining therefore rotational equilibrium, and the body can actually slide down with a constant velocity. Right? So then N into X, that's a clockwise torque of N about O, and it must be balanced by F into A by 2. F into A by 2. In the vertical direction again, there is no acceleration, so N must be equal to mg cos theta. As far as the magnitude of N is concerned, there is no change, status maintained. Only the line of action shifts so as to just counter the effect of the torque produced by F, and the body does not tumble. Right? So N is mg cos theta into X, and F must be mg sin theta. Which gives me X is A by 2 tan theta. That's a shift in the position of the normal reaction, line of action of the normal reaction to maintain rotational equilibrium. Got me? Alright, so we have this accelerated rolling. We have this accelerated rolling of this rigid body on a fixed horizontal surface. Its linear velocity is v naught. Since it's rolling, its angular velocity omega naught must be v naught by r. R is the radius of the biggest sphere, right? That must be its angular velocity. And if it has a linear acceleration a naught, its angular acceleration alpha must be what? A naught by r. A naught by r must be its angular acceleration. Now, let's put the acceleration of the point A in perspective. Alright. By superimposing pure translation with pure rotation, because of pure translation, it shares a common acceleration with the center of mass, and that's A naught. Now, imagine it to be in a state of pure rotation with angular acceleration alpha centered at O, then A would have had a tangential acceleration because of pure rotation with an angular velocity, with an angular acceleration alpha naught. It would have had r alpha perpendicular to this, would have been its tangential acceleration perpendicular to OA. Yes or no? Right? And it also has a centripetal acceleration omega squared small r towards O. It also has centripetal acceleration omega squared small r towards O. So the centripetal acceleration is omega squared small r directed towards O. Omega squared small r directed towards O. Now, what we are seeking is theta such that the resultant of omega squared r alpha and A naught is 0, right? We might want to carry out this calculation in two mutually perpendicular directions that are convenient and easy to deal with. For example, I might choose one direction as the radial direction, the other direction perpendicular to the radial direction, right? Now, this angle obviously is theta. Do you realize that in the radial direction, therefore, in the radial direction, omega squared r must be taken care of by A naught cos theta, right? In the radial direction, net acceleration 0 means omega squared r must be A naught cos theta. Right? And in this direction, A naught sin theta must take care of R alpha. A naught sin theta must take care of R alpha. Right? Now, alpha is A naught by capital R. Alpha is A naught by capital R. So, this alpha you can write as A naught by capital R, and that leads you to sin theta equal to small r by capital R. Right? And now once you have sin theta, you can plug in cos theta as root 1 minus sin square theta, root 1 minus sin square theta, omega squared r, you can write as V naught squared by R squared, V naught squared by R squared, and solve for V naught, solve for, yes or no, right, Siddhant? Right? Now if you recall, is this understood by all? Can I write this off? To calculate the omega of a rigid body, all that was required was velocities of any 2 points on the rigid body. For example, if A was a certain point having a velocity VA, making an angle alpha with the line joining A and B had a velocity VB, making an angle beta with the line joining A and B, right? If this was the information of the kinematic status of any two particles on a rigid body, and if the length AB was L, then to calculate the omega of the rigid body, you would require the relative velocities of A and B along a line perpendicular to AB and then divided by the separation between them. That will give me the omega of the rigid body. So, the omega of the rigid body was obtained as VA sin alpha minus VB sin beta, the relative velocity is perpendicular to AB divided by L. Now, in case VA sin alpha was larger than VB sin beta, omega would be like this. Otherwise, omega would be like this, the orientation of omega. If this was larger, then the omega would have been like this. Because this point B would find A to have a higher velocity. So, it's as if with respect to A, with respect to B, A would be moving like this. And with respect to A, B would be moving like this. So, that means the body would get oriented this way. So, omega would have been like this if VA sin alpha would be greater than VB sin beta. Otherwise, it would be like this. Right? Now, that's the idea in the next problem. So in this system of bodies rolling and no slipping occurring anywhere, look at an upper sphere. Look at an upper sphere. All right. This point P on the upper sphere does not slip with respect to the platform, and therefore the point P has a velocity synonymous with the velocity of the platform, right? The point P on the sphere. Now look at this point Q. This point Q does not slip with respect to the lower platform, so Q has a velocity synonymous with the lower sphere, V. Okay. So now I have 2 points P and Q on this rigid body whose velocities are 2V and V, perpendicular to the line joining them, PQ. Yes or no? And PQ is 2R, right? So the omega of the upper one is going to be the relative velocities perpendicular to PQ, which is 3V, divided by the separation between them, which is 2R. Yes or no? 2V minus V divided by 2R. That's the omega of the upper sphere, right? For the lower sphere, again, the point Q on the lower sphere has a velocity V to the left, and let's say the point P at this point has 0 velocity, because there is no slipping at this point. This is a fixed surface, right? So this has 0 velocity. Now the omega of the lower sphere is going to be relative velocity V minus 0 divided by 2R. V minus 0 divided by 2R. So the omega of the lower sphere is going to be V divided by 2R. So omega upper by omega lower is 3. Omega upper divided by omega lower is 3. Got me? So we have a square lamina. We have a square lamina of side L, and this is the axis about which we want to be able to find the moment of inertia of the square lamina. Okay. Two things about the square lamina, if you remember. One, about a diagonal, the moment of inertia of a square lamina was 1/12 ml square. Remember that? About a diagonal, the moment of inertia was 1/12 ml square. One. Second, look, in your, what does moment of inertia reflect? It reflects physically the mass distribution of mass with respect to the axis. That's what moment of inertia reflects, right? Now, if I chose an axis like this, that means I shift this by an angle theta. That means that this becomes a new axis. Then the change of mass distribution here is negated by the change of mass distribution here, and the moment of inertia remains unaltered. The moment of inertia remains unaltered. That means instead of this diagonal, if you took another diagonal passing through the center of mass, not diagonal, another line, another axis passing through the center of mass, shifted by an angle theta, then the moment of inertia about this will be the same as the moment of inertia about this. The change in mass distribution here is completely opposed and negated by the change in mass distribution here, thereby retaining the same moment of inertia, right? So about this axis also, the moment of inertia is going to be 112 ml square. Clear? Okay. Now, what I do is, I construct an axis passing through the center of mass parallel to this, parallel to this. Center of mass. Right? Now, the moment of inertia about this axis will be 112 ml square. Right? Will be 112 ml square. This axis, of course, makes an angle 15 degrees with the horizontal, and this distance would be half the diagonal. This distance is going to be half the diagonal. The diagonal is L root 2. So this is going to be L root 2 by 2. Right? L by root 2. And the distance between the two parallel axes would be this. AP would be the distance between the two parallel axes. AP would be the distance between the two parallel axes. So then I about this axis is going to be 112 ml squared plus m into AP squared. That's parallel axis theorem, right? So the only task ahead of us is to be able to calculate AP. Now, AP is perpendicular to this line. If this line makes an angle 15 degrees with the horizontal, then a line perpendicular to it would make an angle 15 degrees with the vertical, right? Isn't it? And then this entire angle is 45 degrees. This angle is 45 degrees, which means this must be 30 degrees. This angle must be 30 degrees, yes or no? And if this is 30 degrees, then AP is L by root 2 cos 30 degrees. AP is L by root 2 cos 30 degrees. That's AP. L by root 2 cos 30 degrees is AP, yes or no? Right? And then, of course, you apply parallel axis theorem. I about this axis is going to be 112 ml squared plus m into AP squared. Root 3 L by 2 root 2. That's going to be the moment of inertia about the shown axis. 112 ml squared. I about the center of mass axis, parallel center of mass axis, and m into AP squared. Clear? So we have this solid sphere of mass m, radius r, initially at rest, and is very gradually lowered onto the truck. Now the point of contact has a velocity v0 to the right, whereas that point on the sphere has zero velocity. So initially when you do this, there would be rubbing. Friction would be kinetic in nature between the truck and the sphere. this friction would eventually bring about rolling in a period of time. That's what it would do, right? So from this point till the instant of rolling, you won't expect conservation of energy because friction would have caused rubbing, there would be loss of kinetic energy, right? Let's say one of the things that you realize is that the frictional force acting on this, would have eventually been such that it would have made the velocity of this point same as that of the truck, at the instant of rolling. Would you guess the direction of friction? Although we can do that without that also, but just for the heck of it, can you initially, when I lower it onto the truck, what would you estimate as the direction of kinetic friction acting on the sphere? Right, left? Huh? Right. I mean, if there was an observer sitting on the sphere at the point of contact, it would find that the truck is moving to the right. So it would exert on the truck a leftward friction force. So the the truck would exert on the sphere a rightward frictional force. Isn't it? Right? So that's ordinary common sense, although it's not required to know that. We could, but you should have an understanding, right? So one thing, frictional force acts to the right. It would build velocity of the center of mass rightwards, right? This F would create an acceleration on the center of mass, would build a velocity of the center of mass rightwards, and would exert an anti-clockwise torque about the center of mass, and therefore an anti-clockwise alpha would yield, and then you would expect an omega in this sense to develop. Right? The other way of looking at things is, when rolling seeps in, look, when I just lowered it onto this point, right? Frictional force, irrespective of whether it was acting to the right or it was acting to the left, it passed through the point of contact. It never produced any torque about the point of contact. mg passed through this point of contact, never produced any torque about the point of contact. Normal reaction from the truck passed through the point of contact, didn't produce any torque. Therefore, about the point of contact, the angular momentum of the sphere must have been conserved, whether it's from the initial state to some intermediate state or till the state of rolling. Between any two states, for sure, angular momentum about the point of contact must have been maintained. Right? Now, when you lower it on, then the velocity, both linear and angular, of the sphere is 0. So its angular momentum about the point of contact is 0, yes or no? Right? So after a while, when rolling starts and the sphere develops a rightward velocity v, then this rightward velocity v about the point of contact would have produced a clockwise angular momentum, would have produced a mv into r clockwise, right? But the net has to be 0. So to counter this clockwise angular momentum, its omega must have been like this, anti-clockwise, so that the ICM omega anti-clockwise about the point of contact and mv into r, they add up to 0. At the instant of rolling, therefore, you would expect, when this is the state of rolling, well, mv into r, the clockwise angular momentum, and then ICM omega, anti-clockwise angular momentum, they must be equal to the initial angular momentum about the point of contact, which must be, right, where ICM is, for a sphere, 2/5 mr square. ICM is 2/5 mr square for a solid sphere, 2/3 mr square for a solid. Now, this of course is purely conservation of angular momentum, and this does not even speak of rolling conditions. This is, I mean, even if this was not a rolling condition, it was some intermediate state, you would expect this to be 0. Right? So the rolling fact is not yet built into the situation. We will have to put together pieces of rolling together and write an equation commensurate. Now, if realize that this was V, this was omega, and let's say this was a state of pure rolling. Then if I superimpose, then the velocity of the point of contact because of pure translation would be V rightwards, and because of pure rotation about the center of mass would be R omega rightwards. So V plus R omega, yes or no? V plus R omega, and this V plus R omega, in order that there is no slipping, must be equal to V naught. If this is the state of pure rolling, then V plus R omega must be the same as the velocity of the drop. Yes or no? Velocity of the point of contact must be the same as the velocity of the surface for a rolling requirement. Yes or no? So this must be equal to V naught. That's rolling. Right? So now we have essentially just two unknowns, V and omega, and we can obtain. Got me? Now, even if you are indiscriminate about the choice related to the direction of omega, I mean, if you had selected omega carelessly, clockwise, does not matter, because then you would still have MVR plus ICM omega equal to 0, right? Which would cause omega to eventually become negative. So, and then if omega was like this would then become V minus R omega equal to V. It will not matter. The sign of omega, as is appropriate, would automatically be thrown out for your consumption. Even if you were absolutely callous about the sense of omega, you didn't break your heads over it. I mean, you could have arbitrarily selected the direction sense of omega, and the right sense would have appeared automatically with its sign, right? I have spoken of the instantaneous center, right? Very sleepy, right? Yes, you are. You want some water? Want some soda? No? So this is a ladder, and this end of the ladder is moved to the left with a velocity v. The point B obviously slides along the inclined wall, right? And we want to be able to find the angular velocity of the ladder at such an instant. It's obviously in a state of general rigid body motion. Best thing to do here is to obtain the instantaneous center. If you have knowledge of the velocities of any 2 points on a rigid body in general motion, then all that you need to do is draw perpendiculars to those 2 directions. The intersection of those 2 perpendiculars would locate the instantaneous center. The body could be imagined to be in a state of pure rotation about the instantaneous center, right? So, draw a line perpendicular to V. Draw a line perpendicular to the velocity of B. The velocity of B, of course, we don't know the magnitude of the velocity of B, but we know for sure because of the physical constraint. B is poised to move along the So then draw perpendicular to this. And the intersection of these two perpendiculars to two known directions of velocity will locate the instantaneous center P, will locate the instantaneous center P of the rigid body. This angle is 30 degrees. As you can see, exterior sum of two interior opposite angles. This 60 degrees. This 60 degrees. So PAB is equilateral. PAB is equilateral. And therefore, this length must be L. Right? And imagine it to be in a state of pure rotation. A certain point has a velocity v. So v must be L omega. V must be L omega. So omega must be v divided by L. I mean, think of P as yet another point whose velocity is 0. This is a point with 0 velocity. So 0 velocity, this point A has velocity v, and the relative velocity perpendicular to AP divided by the length L will give you the omega of the rigid body. V minus 0 divided by L will give you the omega of the rigid body. That's what you do. So this mass passing over this pulley, and this initially held horizontal. So when it's just about release, you would expect M to have an acceleration A downward. M is acted upon by two forces, mg and T. Mg minus T would give me, that's as far as this body is concerned, right? Now because of the string constraint, the point B has an upward acceleration, right? At this instant, you would expect the point B to be moving in a circle of radius L centered at A. At this instant, for this instant, you can imagine the point B to be moving in a circle centered at A and having radius L, and the point B has a linear acceleration A. Therefore, the alpha of the rigid body is A by L. Is the angular acceleration at this instant A by L is the acceleration of the rigid body? Yes or no? Now, essentially then what produces the angular acceleration? The torque, because of various forces acting on the rigid body. What are the various forces acting on the rigid body? Well, there is a reaction at A. Right? This is a hinge. There is a reaction at A. There is ng downwards and there is tension upwards. Right? So, in order that we could dispense away the reaction at A, we want to take torque at A. Right? So that the reaction at A becomes inconsequential towards our computation of torque. ठीक है छोड़ All right. So we want to be able to find the acceleration of the block just after the release from this position. So as far as this m is concerned, this is the equation. Mg minus t is m into a, and it's ideal to take torque about a so that we can dispense away the reaction at a, right? Realize that for B, there is a tension T, there is mg acting like this. This is the point A, right? And alpha is the resultant of the net torque about A, right? Net torque about A in this sense is T into L minus mg into L by 2 must be I about A, which is 1/3 ml squared into, where alpha can be written as A by L, etc. And then you have equation 1, equation 2, where alpha can be replaced by A by L, and you can solve for clear? There is this L-shaped structure, length 2L and L, placed on a rough horizontal surface and pulled with a force F, so that the rod slides with constant velocity, and we want to be able to find this angle alpha, if it has to slide with constant velocity. Since AB and BC are sliding on a rough horizontal surface, there is frictional force acting leftwards, and maximum static is acting on both AB and AC and BC. Very clearly, if the mass of this is m, the mass of this would be 2m, right? Frictional force on it would be acting leftwards and would be of magnitude 2 mu mg, right? That would be the frictional force through the midpoint of this, and the frictional force through the midpoint of this would be mu mg acting leftwards, right? Since this L-shaped structure is not getting reoriented, the net torque about B must be 0. The net torque about B must be 0. F produces no torque about B. So the torque because of 2 mu mg and mu mg about B must be 0, right? So this angle is theta. This will be theta. Now this length is L. So this length is L sine theta. Is L sine theta. And the anti-clockwise torque of 2 mu mg about B is 2 mu mg into L sine theta. Right? That's the anti-clockwise torque that 2 mu mg produces about B. And it must be countered by the clockwise torque that mu mg produces about B. Now this length is L by 2. So this length is L by 2 cos theta. And the torque of mu mg about B is mu mg into L by 2 cos theta. Right? And that gives us tan theta equal to 1 by 4. Tan theta is 1 by 4. So this angle alpha is going to be pi minus theta, which is pi minus tan inverse 1 by 4. Pi minus tan inverse 1 by 4 is going to be this angle. Clear? Make sense? So we have this uniform rod of mass m, length L, initially at rest, making an angle 30 degrees with the vertical and release. Right? At the instant of release, we want to be able to find the normal reaction at A, acting from the ground on this rod, right? Say N is the normal reaction that we are seeking, right? The only other force acting on the rod is mg downwards. There is no frictional force because this is a smooth surface, right? These are the only two forces. Whatever is happening on the rod is an outcome of N and mg, right? Now, this is the center of mass. The difference of mg and n causes the center of mass to accelerate downwards, right? So, let's say the acceleration of the center of mass is ACM downwards, and that happens because of mg minus n that produces ma. Equation 1. mg minus n is MACM. Yeah? Then there is also a torque about the center of mass. mg produces no torque, but n will produce a non-zero torque about the center of mass, and the torque of n about the center of mass is clockwise, as you can see, and that produces a clockwise angular acceleration alpha. Clockwise angular acceleration alpha. Now, to calculate the torque, what you do is you resolve n as n sine 30 degrees perpendicular to the rod and n cos 30 degrees parallel to the rod. N cos 30 degrees has its line of action passing through the center of mass, will therefore not produce any torque about the center of mass. N sine 30 degrees will produce a torque n sine 30 degrees into L by 2, and that must be ICM alpha. N sine 30 degrees into L by 2 must be I about the center of mass into angular acceleration alpha. Clear? That's a clockwise torque because of n sine 30 degrees. That must be I about the center of mass, which is 112 ml squared into angular acceleration. So we have represented translation, we have represented rotation. Now, what are the unknown devils here? N, ACM and alpha. 3 unknown devils, and we still don't have enough number of equations. We have only 2 physical conditions represented here, but 3 physical entities to be known, which means there is some physical condition which is yet to be represented. Some physical conditions still not put in place. What is that physical condition not yet put in place? Huh? Huh? Alpha is not 0. It has a n is not 0. How can alpha be 0? Alpha, huh? Alpha is no. Hmm? If it was fixed about the center of mass, then A is L, distance times alpha. One physical, don't think physics, think like a commoner. Think like a commoner. One fact, one physical fact. We'll look at the mathematics and physics of that fact later on. But one stark fact, which still has not found a representation in these 2 equations. Huh? I mean, this is a rigid body, so that's fine. That just causes it to be a rigid body, which is all right. Distance, but no distance. We're talking of an instant, so we are not talking of a distance. Sometimes you will have to forget all the physics that you learned. You will have to think like a lay person. Well, the point A cannot move upwards. It has no vertical acceleration. That has not been represented anywhere. The acceleration of A must be along the ground, must be parallel to the ground. Yes or no? I mean, if you leave a rod like this is a smooth surface, right? The point A will not jump up. Do you realize what I'm saying? The acceleration of A in the y direction must be 0. The acceleration of A in the y direction must be 0. That fact has still not been represented. That's the physical fact that requires mathematics, right? Okay. Now, how does one conventionally find the acceleration of a certain point? Then look at the center of mass that has an acceleration ACM, right? And this has an angular acceleration alpha, right? Now this point A, because of pure translation, it will share a common acceleration ACM with the center of mass first, which is downwards, right? I'll superimpose everything, all the effects. And then imagine it to be in a state of pure rotation about the center of mass with angular acceleration alpha. Then it would have a tangential acceleration L. This is L by 2. Alpha would be its tangential acceleration. Yes or no? Tangential acceleration R alpha. Imagine it to be in a state of pure rotation about the center of mass with angular acceleration alpha. This would be perpendicular. Yes or no? This angle is 30 degrees. So this would be 60 degrees. Right? Isn't it? The velocity of this point is 0. So it's not going to have any centripetal acceleration. At this instant, it starts from rest, no sense. So these are the only two components of acceleration, right? And in the vertical direction, L alpha by 2 and ACM must add up to 0. So L alpha by 2 cos 60 degrees must be ACM, yes or no? L alpha by 2 cos 60 degrees must counter ACM so that the vertical acceleration of this point is 0. So vertical acceleration of A 0. Would mean L alpha by 2 cos 60 degrees equals ACM. And now we have the required number of equations to deal with. In this case, realize ACM is not L by 2 alpha. Some of you initially thought, right? So, we're done with this, right? So, this is a uniform rod of length L kept against a smooth wall and smooth floor. What's the angular acceleration of the rod just after the release? So, we are seeking angular acceleration, we would think of tau equal to I alpha. You think of tau equal to I alpha, and in general rigid body motion, the two eligible points towards application of tau equal to I alpha are instantaneous center and center of mass. Let's keep that open-ended right now, whether we're going to choose the center of mass to apply tau equal to I alpha, or whether we're going to choose the instantaneous center. Prior to that, let's have the forces in place, the forces acting on the rigid body, right? What are the forces? That means the free body diagram, right? The free body diagram means there is weight acting downwards. There is going to be normal reaction from A acting upwards. And there is going to be normal reaction from B acting leftwards. No friction, smooth surfaces. This summarizes all the forces. Now the issue is, if I took tau equal to I alpha for the sake of calculation of alpha about the center of mass, then would be nagging issues. Then I would have to deal with NA and NB, isn't it? Not a good idea, therefore, to take torque about the center of mass, because then NA and NB would cause problems. Let's locate the center of mass. The point A is constrained to move leftwards. A line perpendicular to the velocity of point A is this. Point B is constrained to move downwards. A line perpendicular to the velocity of B is leftwards. This therefore must be the instantaneous center. The body could be imagined to be in a state of pure rotation about the instantaneous center. This then, the point P is the instantaneous center. And now the merit in taking torque about P is that line of action of Na passes through P, line of action of NB passes through P, they end up producing no torque about P, so not a problem. Then the only force that produces a non-zero torque about P is mg. Yes or no? So then, to calculate the torque about P, I have mg into this length, mg into this length is the same as this length, and realize that the torque about P would be like this, causing an angular acceleration alpha to have this sense, right? So the angular acceleration is going to be mg into, realize that this length is theta, this angle is theta, so this is going to be L by 2 cos theta. So mg into L by 2 cos theta is the torque about P divided by I about P. I about P. Yes or no? Now, do you realize that this distance is L by 2? This is L by 2, right? Huh? So then, I about P is going to be I about Cm plus m into L by 2 square, isn't it? I about this axis is going to be I about the center of mass axis plus m into L by 2 square, right? So I about P is no, I about P is I about the center of mass, m into L by 2 squared, and I about the center of mass is right. You can plug in that and calculate the value of alpha. So, it becomes very crucial and critical to be able to judge the point about which you want to apply tau equal to I alpha. In both cases, both roads would lead to Rome, but then one would do it in a manner much simpler than the other, right? So, at home when you're practicing problems, when you have an option of applying tau equal to I alpha, try both the points so that you have a mental comfort with both kinds of things. You are actually able to distinguish between the good and the not so good in terms of the algebra produced. One would lead to very simple algebra, the other one might really give you some complications, right? So we have a stationary disk resting on a smooth frictionless surface, and there is an insect of 1/3 the mass of the disk at this point, and it starts to move in this direction. Now, when it starts between the insect and the disk, the total angular momentum about the center of the disk was zero initially, because both were at rest, right? And if you look upon them as one single unit, then the angular momentum will remain preserved. So if the insect manages to move circumferentially like this, then the disk must move in this direction so that their angular momenta about to cancel off from instant to instant. You know what I'm saying? Now, if at a given instant omega I is the angular velocity of the insect in this direction and omega d is the angular velocity of the disk in this direction, then one thing that's evident is, it's from the data given, if the angular acceleration of the disk is 2 pi, then the omega of the disk at any given instant of time is going to be omega equal to omega naught plus alpha t. Omega naught is 0 for the disk, so it's going to be 2 pi t radians per second for the disk at any given instant, right? Now, the angular momentum that the insect has about O is going to be, the moment of inertia of the insect about O is going to be, well, its mass m by 3 into r squared. It's going to be the moment of inertia about O of the insect, I into omega I. That's going to be the angular momentum of the insect about O, and that must be cancelled by the angular momentum of the disk about O. And the angular momentum in pure rotation of a rigid body about O is going to be I about O into omega. I about O for the disk is going to be mr squared by 2 into omega of the disk. Yes or no? So the two angular momenta are opposite and of the same magnitude, and therefore the net angular momentum about O for the insect plus disk remains 0 instant to instant. This gives us an opportunity to calculate omega I in terms of omega t, given that omega t at this instant is 2 pi t, right? So we have very clearly omega I equals 3 by 2 omega d. Omega d is 2 pi t, which is 3 pi t is the omega of the insect, right? Now, think of the motion of the insect with respect to the disk, as if the disk is at rest, and the insect has an omega. So if you look into that with respect to the disk frame of reference, then the omega relative of the disk is going to be omega I minus omega d. That means 3 pi t minus 2 pi t, that means 5 pi t would be the angular velocity of the insect with respect to the disk, yes or no? And so it's as if the disk is at rest and the insect has an angular velocity omega with respect to the disk. So then the insect, because of this omega, would cause this theta with respect to the disk to change with time. Theta is the angular displacement with respect to the disk of the insect. So then can I say omega rel must be d theta dt, where theta is the relative angular displacement with respect to the disk of the insect, right? Which gives me like 5 pi t equals d theta dt. Theta is the relative angular displacement with respect to the disk of the insect. And when I integrate, theta is 0 at time t equal to 0. When I integrate, I end up getting theta equal to 5 pi t squared by 2. Right? Now, when the insect comes back to the same point on the disk, then the theta with respect to the disk must have been 2 pi. When the insect comes back to the same point on the disk, then the angle that it has described with respect to the disk must have been 2 pi. So if you put theta equal to 2 pi, you will get the time when the insect arrives at the same point on the disk. If you put theta equal to 2 pi, right? Then you will get the time t at which the insect arrives at the same point. Just put theta equal to 2 pi, then you will get the instant t required. Now in this time t, once you have the time t, by plugging in theta equal to 2 pi, the angle rotated by the disk would be initial angle plus half alpha t squared. Half alpha t squared. Theta rotated by the disk as seen by the ground would be initial theta of the disk 0 plus half alpha of the disk, which is 2 pi, into t squared, which is obtained from here by plugging in theta equal to 2 pi. Right? So that's the angle rotated by the disk. Does that sound alright? So we have this rod AB on a horizontal surface in general rigid body motion. The center of mass has a velocity UCM and it has an omega, right? So the center of mass, of course, continues to move with along a straight line with a velocity UCM, while the rod keeps getting reoriented with time, right? And the reorientation phenomena is managed by omega. So time it takes to come back to the vertical state is 2 omega. By the time the rod gets its orientation restored, the center of mass would have drifted a certain distance to the right, and the point B would have also traveled a certain distance. A certain point B here would have traveled a certain distance. In this problem, we are seeking the distance traveled by the point B by the time the rod gets reoriented back to its original state. That means in time t equal to 2 pi by omega, what's the distance covered by B? Now, after a while, the rod would have got reoriented by an angle theta with respect to its original vertical state. So, at a certain intermediate instant, call it t. This was t equal to 0. This was a certain instant of time t. The rod would have got reoriented by an angle theta. The rod would have got reoriented by an angle theta. A would have come to A prime, B would have gone to B prime. Right? That's what would have happened. The center of mass would be like a UCM to the right. Would it be a UCM to the right? And it would still have an angular velocity omega. At this juncture, let's put the velocity aspect of B in place. Right? Velocity of B by superimposing. Because of pure translation, it's going to have a UCM. Imagine it to be in a state of pure rotation about the center of mass. Imagine it to be in a state of pure rotation about the center of mass with angular velocity omega. Then this will have a velocity perpendicular to this length, and equal to L by 2 omega. This velocity would be L by 2 omega, right? This velocity, tangential velocity, because of pure rotation about the center of mass, is going to be L by 2 omega, yes or no? Very clearly, if this makes an angle theta with the vertical, a perpendicular to it would make an angle theta with the horizontal, right? Now, the point B therefore has a velocity UCM like this, has a velocity L omega by 2 like this, and the angle between these two is pi minus theta. So the net velocity of the point B at this instant can be obtained. This would be the net velocity of the point B obtained from the parallelogram law, right? And the angle between UCM and L omega by 2 is pi minus theta, right? So can I say that VB squared from parallelogram law is UCM squared plus omega L by 2 squared plus twice UCM into omega L by 2 cos pi minus theta. Cos pi minus theta would be minus cos theta. Minus cos theta would be this. But it's given that UCM is omega L by 2. This omega L by 2 is given to be equal to UCM for the given problem. So what you might want to do is replace this omega L by 2 by UCM. So then this becomes 2 UCM squared minus 2 UCM squared cos theta. Like 2 UCM squared. 1 minus theta is 2 sine square theta by 2. Which leads to the velocity of the point B as 2 UCM into sine theta by 2. 2 UCM into sine theta by 2 is the velocity of the point B at this instant, where theta in time t must have been omega t. The angle rotated by this rod in t seconds must be omega t. Yes or no? Omega determines the extent of orientation that has occurred. Theta therefore must be omega t because omega is remaining constant with time, right? So theta is omega t. So this you can write as 2 UCM into sine omega t by 2. That's the velocity of the point B at an instant of time t. Now, obviously then it's a function of time. It's not a constant velocity. It's not a constant velocity. So in dt seconds from this instant, the distance covered by B is going to be Vb into dt. Right? That's the distance covered by B in dt seconds from now. So the total distance covered by B is going to be integral Vb dt, where t runs from 0 to 2 pi by omega. T runs from 0 to 2 pi by omega. Yes or no? Easy to integrate. Vb you can plug in as 2 UCM sine omega t by 2 etc. dt, and you can readily integrate to find the distance covered by t. What's the distance covered by the center of mass? UCM is the same into 2 pi by omega. Omega L by 2 into 2 pi by omega would be the distance covered by the center of mass in that time. The velocity of the center of mass is not a function of time in this case, but the velocity of v is changing with time, right?